I am David Falliano, a postdoctoral researcher at the Polytechnic of Turin. In the contribution I am going to show you, I'll present some results of an ongoing research focused on a special concrete called formed concrete. The title of the contribution is Strategies to Increase the Fracture Energy of Formed Concrete. Formed concrete belongs to the category of lightweight concretes. Lightweight concretes can be characterized by a density ranging from 150 kg for cubic meter to 2000 kg for cubic meters. In general, there are several ways to produce lightweight concrete. In case the density reduction is obtained through the addition of air bubble in the cementitious matrix, we have cellular concretes. More in particular, if the air bubbles are obtained through the addition of preformed foam into the cementitious matrix, the resulting special concrete is called formed concrete. In fact, as illustrated on the slide, elements forming formed concrete are cement, water, stable foam, fine sand, and, if necessary, additives. These elements are simple, cheap, and easily available, and this allows this material to be very convenient from an economic point of view. The preformed foam mixed with the cement paste give rise to the development of a system of air voids in the material microstructure, giving formed concrete the peculiar characteristics common to all cellular materials, namely thermal insulation, especially when low densities are used, sound absorption, good resistance against fire, flotation, when the density are lower than 1000 kg for cubic meters, but above all, lightness. Therefore, foam is the ingredient that characterizes these cementitious materials, and it's created by trapping pockets of air in a liquid phase in order to obtain so-called liquid foams. In general, liquid foams are composed by a solution of water and surfactant expanded with air. Surfactant molecules, which are amphiphilic, prefer to be present at the interface air fluid, as illustrated on the slide, and they arrange themselves so that the tail groups, which are hydrophobic, are in contact with the air, while keeping the head groups, which are hydrophilic, within the liquid. Therefore, they play the fundamental role of increasing the lifetime of a foam. The most relevant properties of a foam to be used for the preparation of formed concrete are density and lifetime. The latter is associated with the drainage, which represents the most destabilizing cause for a foam. These parameters are significantly influenced by nature and concentration of foaming agents and by the air pressure used to produce the foam. In this slide, you can see the homemade foam generator that we used to produce the preformed foam. First of all, water, whose input is indicated by point 1, and surfactant, input indicated by point 2, are mixed. The surfactant concentration is adjusted by the metering pump illustrated in point 3. After, the water surfactant mixture meets the compressed air, whose input is indicated with point 4 and whose pressure is regulated by the pressure reducing valve in point 5. Lastly, the water surfactant mix expanded with compressed air passes through the mixing pipe that's filled with appropriate brass rings that trigger the turbulent flow conditions and make it possible to obtain an homogeneous and stable foam whose output is indicated by the point 7. Generally speaking, both an increase in foaming agents concentration and an increase in air pressure used to generate foam lead to a decrease in both density and drainage of the foams produced. For a more in-depth study of this topic, you can refer to the recently published article shown on slide. An increase in foam's volume in the mix proportion will lead to a decrease in cementitious material's density and consequently to an increase in its porosity, since air bubbles will occupy a greater part of the volume. Density and porosity play a fundamental role in defining properties of foamed concrete. The higher the porosity, or that is the same, the lower the density, the better the properties of foamed concrete in terms of lightness, thermal insulation, sound absorption and fire resistance, which are characteristics of absolute importance in the building sector, but, on the other hand, the worse the mechanical strength. After this very short presentation of the material, the next part of the presentation focuses on the experimental evaluation of the fracture energy of foamed concrete. In particular, two different strategies to improve the fracture energy of foamed concrete will be presented. The first is linked to the curing condition stage, the second to the beneficial effects of the addition of an eco-friendly material, namely biochar. In addition, the results in terms of flexural and compressive strength will also be presented. In all the presented cases, the specimens were prepared according to the standard shown on the slide. Prismatic beam specimens of 20 mm x 20 mm x 80 mm were tested under crack mouth opening displacement controlled tip-point bending tests. A displacement rate of 0.005 mm for minutes was used. At the end of the flexural test, the two halves of the broken prisms were tested in compression with a displacement rate of 0.5 mm for minute. The fracture energy is computed through the formula shown in the slide and reported in the standard, to which reference should be made for all the details. As anticipated, strategy 1 consists in choosing the best curing condition to obtain a higher fracture energy. For this first strategy, the specimens were prepared using a Portland cement of class of resistance equal to 52.5 R and a fixed water to cement ratio equal to 0.3. The preformed foam, which density was equal to 85 grams per liters, was generated through the foam generator using a protein foaming agent concentration equal to 5% and an air pressure of around 3 bar. The final foam to cement ratio to obtain the target density of 800 kg for cubic meters was equal to 0.3. Two different curing conditions were considered. In fact, half of the specimens were immersed in a water tank at a controlled temperature of 20 Celsius degrees, while the other half of the specimens were cured in air at environmental laboratory conditions. Before the test, the beams were notched through an appropriate saw in accordance to the prescriptions of the standard. After the tests, all the specimens were placed in a oven and dried at 110 Celsius degrees until the achievement of a constant weight in order to evaluate the dry density. From the experimental results illustrated in this slide, it is clear that the curing conditions play a crucial role, especially in cases of flexural strength and fracture energy, while the difference is less significant in the case of compressive strength. In particular, samples cured in air have a mean fracture energy that is more than 3 times higher than those cured in water. Taking a look to two representative specimens corresponding to the two different curing conditions, it is possible to notice that the crack path is quite similar, but the crack surface looks slightly different in the two cases, showing a more evident tortuosity in the air-cured specimens than in the water-cured ones. This macroscopically justifies the higher fracture energy achieved in air-cured specimens. Coming to the microstructural analysis through spasm, in contrast to ordinary concrete, in which a main crack is usually identified, for formed concrete specimens cured in air, a diffused crack pattern is noticed, which is characterized by a widespread microcracks developing throughout the crack surface. On the other hand, specimens cured in water exhibit less diffused microcracks and a smoother crack surface, which implies a lower fracture energy and a resulting different flexural behavior. The phase micrographs reported in this slide highlight how the curing conditions affect the development of different hydration products. In fact, in air-cured samples, a peculiar mono-oriented straight shape typical of flat crystal is noticed, while in water-cured specimens, flower-like crystals prevail. The different fracture behavior between the two curing conditions is then the result of such distinct morphological characteristics and microstructural differences. As already said, strategy 2 consists of an eco-friendly addition to the cementitious matrix, that is, the addition of biochar. In particular, two different concentrations of biochar were studied, 2% and 4% of cement weight. Compared to the previous mixed design, in this case the chosen target dry density was equal to 1,600 kg for cubic meters. In fact, studies concerning lightweight formed concrete with the addition of biochar are currently in progress and will be shown in future works. The results of the experimental tests in terms of flexural strength, fracture energy, and compressive strength are reported in the table presented in this slide. The addition of biochar at 2% concentration seems to be beneficial in improving the fracture behavior of formed concrete. In fact, there is an increase of the fracture energy of about 10% with respect to the reference samples. Contrarily, the increase of biochar up to 4% gives rise to a slight decrease of about 4% in the fracture energy values compared to the lean samples. This result is justified in view of the modifications of the fracture path provided by the biochar additions in the formed concrete microstructure and in view of the fact that, unlike biochar at 4% concentrations, the presence of the 2% biochar doesn't produce a decrease of the flexural strength. However, in any case, the addition of biochar gives rise to a significant decrease in performance in terms of compressive strength. In conclusion, in this contribution, two different strategies to improve the fracture energy of formed concrete were presented. The first strategy is the choice of the curing condition, the second one the addition of biochar. With regard to strategy 1, it was highlighted that the air curing condition results in a significant increase in both the fracture energy and the flexural strength. Instead, the compressive strength with the two different curing conditions are comparable. The different fracture behavior between the samples cured in air and in water is the result of distinct morphological characteristics and microstructural differences. With regard to strategy 2, the addition of biochar at 2% concentration with respect to the cement weight results to an increase of the fracture energy of about 10%. Further biochar additions do not translate into increases in fracture energy. Moreover, the addition of biochar always results in a significant decrease of the compressive strength. The utopia in the construction field is to realize a material characterized by lightness, very good mechanical properties, excellent performance in terms of fire resistance and thermal insulation, and low environmental impact. Formed concrete may represent a real solution, but much more research is needed to improve its performance. Thanks for your attention.